So good morning, everybody, and welcome to the Diving into NumPy tutorial. I am very glad to have here with us David Cournapeau and Stefan van der Walt, that they have been long-time contributors to the NumPy project. David, he's French. He, in particular, has been producing releases of NumPy by several years. And I can assure you that this is not an easy thing to do. So, and then Stefan van der Walt, I think he contributed a lot, especially on the documentation side, that I think it's a critical part of every library, and especially a critical part of the scientific stack, like NumPy. So you can proceed when you want. Okay.
Okay. Yeah, thank you.
I thought you had.
Yeah, no, I don't. Okay, can everybody hear me well? Yeah. Okay, so, well, just to make sure like everybody's at the right session. So this is for like diving into NumPy. So the idea is, let's say you want to spend a bit sometimes, you would like to contribute to NumPy, but you don't really know where to start because NumPy codebase is a bit complicated. Like, the hope is that after these 4 hours, after like Stefan's presentation and my presentation, we get a better idea of like how NumPy is implemented, how does it work, and like how can you start like doing like a few things. Like one of the goals is to give you the ideas that fixing bugs into NumPy, even the C part of the code, which is harder than Python usually, still not that can be pretty hard, but it's not as hard as you may think. So if after the 4 hours you get back the ideas that, oh, okay, now I have a decent idea on how to fix simple bugs into NumPy, well, we will be at least partially successful. Okay, so yeah, the goal is to learn a bit like how NumPy works. Like, so I don't know how many of you have already like read a bit, look into the NumPy code base, especially the C code, but well, some parts are a bit like dark corners and it's not as well documented as it should be. Like, it's not always obvious what does what and like where things are located. But I hope at the end of the 4 hours, you will be more like this guy. We'll have some ideas. We have like this big mess, but at least you have a bit of a thread of like hope, understanding a bit how some things work and how to fix something. So, okay, concretely, what the goal here is, so one big, that's always the case with a big code base like NumPy, is just finding your way into the code base is not obvious. Like, we don't have a really good explanation on what is where. So part of the goal of this presentation is to give a better idea of, like, there's this thing in NumPy I'm interested in. I don't even know where it is implemented. Hopefully at the end of the presentation, you will have a better idea. Okay, that's where things are. We like also give a few tools, like, or a few advices on how to work efficiently on NumPy. Like when you have something that doesn't work on NumPy, you want to fix something on NumPy. Like it can be pretty easy to waste a lot of time doing simple things because you have a lot of input in C. There's a Python C interface, which can be tricky to understand. So we'll give a few advice on how to deal with that. And concretely, like what we will do, like today, hopefully we'll fix one real NumPy bug. There will be implementation of some new array methods in NumPy, how to implement your own ufunc, and the basics of implementing your own D-type. So it's a bit difficult because there is a C code, but still we try to do like quite a few exercises so to really like practice and get a better idea of how to do things in the NumPy code base. Okay. So before actually entering to NumPy, I want to give like a big like warning because it's easy like after you spend like 4 hours on NumPy like tutorial and you're like, oh great, no, I know everything there is to know about NumPy C code, and now I will write everything with NumPy C code. It's actually a pretty good like way of thinking that generally you shouldn't extend NumPy, you should write a library that use NumPy, and you shouldn't do it in C if you don't have to. So really, like most of the time, you don't want to modify NumPy. You really want to implement things outside NumPy. So even so, I hope you will get a better idea on how to do things. You will still see it's pretty tedious to do like simple things. Like things like you take 2 or 3 lines in Python, you can take like hundreds of lines in C. So you don't really want to do that unless you really have to. So when is it appropriate to actually look into NumPy codebase and to modify the NumPy codebase? Well, obviously, if you want to fix a NumPy bug, like there is a NumPy bug, the bug is into the C code, then yeah, okay. In this case, you have obviously to look into the C code. And one of the exercises today is to fix an actual bug in the NumPy codebase. So hopefully, at the end of the presentation, you will actually have fixed one bug in the NumPy codebase. If you want to improve like some existing NumPy features, so by improving, I mean maybe like things are too slow. And like the things that are slow are like really low level. Like, so for example, a well-known issue with NumPy today is like scalar array. So array with only one item in it, they are pretty slow. Like if you have a scalar array, A, and you do like A plus A, that's like at least 1 order of magnitude slower than if you have a float, Python float A. So like how to fix that, how to improve this. Hopefully after these 4 hours, you will have a better idea of if you want to spend time on that, like how to like start doing this. Oops, sorry. And of course, to follow this tutorial, you need to modify the NumPy C code base. So. Okay, so I will not spend too much time on this. It's like to set up the Vagrant VM I gave into the USB key. So I don't spend too much time on it because we will go into that at the exercise. It's just to tell you there is just instruction. That's the slide number 15. So if you want to set up the Vagrant VM that contains all the tools we will talk about, you can just copy everything that is on the USB key and follow the instruction on slide 15, which is on the web on this short URL. You don't have to use the Vagrant stuff and for the virtual machine to do the tutorial, but like some of the tools can be a bit tricky to set up. So for people who are not super familiar with compiling NumPy, and we'll talk a bit about like some tools to get like debugger and these kind of things. If you don't have that set up on your machine, it may be easier to just use Vagrant. Hopefully the USB key contains everything, at least if you're on Linux and Mac, to get up started. So slide 15, that contains all the instructions you can follow during the presentation. Okay, so I will let Stefan do the first part. So the first part is why we let Stefan actually introduce. But the idea is like to give a broad view of the basics of NumPy, just to be sure we all talk about the same thing, and we'll use the concept in the first part in all the successive parts later.
Good morning, everyone. So like David said, NumPy has got a rich number of concepts. And in order to have a conversation about this today, we need to speak the same language. So for the next few minutes, I'm just going to give you a brief overview of the type of topics you might typically find in an advanced NumPy tutorial. So if you're listening to me and you think that's actually more the kind of stuff I would like to know, then we've got several tutorials available online. So you could go, for example, to SciPy-lectures.github.io, and there you will find a bunch of lectures from the previous SciPy conferences. So that's SciPy-lectures.github.io. And I've got several, if you're interested, feel free to get in touch. I've got several other tutorials focusing more in depth on these topics. So I'll give a broad discussion of data types, and then some properties of arrays like strides, which become quite important when you manipulate arrays, broadcasting, and then how do you use indexing with broadcasting. Yeah, sure. So there's a URL over there, bit.ly/diving into NumPy. So if you go there with your browser, those are just the newest versions of the slides in the USB. Yeah, it's just an HTML presentation, so just load it up in your browser. All right, so Python has got a number of numeric types, such as integers and floats and so on, but it's only got one type for each class of number. Now, when we're doing numerical computation, we need a system that is slightly more sophisticated and that can capture many different types of scalars. So NumPy has got this rich hierarchy of array scalar types. So if you look at this hierarchy, you'll see that there's sort of the generic scalar, and then it branches out into all the different kinds. So on the one side, we've got our integers, and then the floating point numbers, and over here, the slightly more unusual ones of string and Unicode and so forth. You might miss some familiar names like NumPy.float32, NumPy.float64. It's because there are many equivalent ways in NumPy of referring to the same scalar type. So for example, what is shown here as single would be np.float32. Float underscore, all the underscore types are types that correspond to Python's built-in numerical types. So the float in Python corresponds to float64 in NumPy. And yeah, so all these underscores, the int underscore, float underscore, there you see NumPy's built-in Boolean type, which is quite different from the one used in NumPy, but they're all organized in this tree. So if you wanted to check whether a scalar that you're working with is an integer, you can simply see whether it subclasses from np.integer, and that will give you the answer. Right, so we've got this rich number of different scalar types, and we use these to build data types. So data type is what you attach to a NumPy array to tell you how the numbers are stored in memory. So for example, if you've got 64-bit integer, then you're using 4 bytes in memory, and those bytes may be ordered in different ways, and NumPy needs to know how they are stored in memory. So the data type tells the NumPy array more about that information. So here I've put up an example of how to construct a data type from float32. So if you call np.dtype and you give it any of those arrays, those scalar types, then it constructs a data type for you, and then you can manipulate things like the byte order. Now, importantly, all NumPy arrays have the same type. So if you literally type x, where x is a NumPy array, then you will always get back nd array. Of course, unless you subclass the NumPy array or so, in which case it will get a different name, but mostly NumPy arrays are always of type nd array. And then the nd array object has got a data type associated with it. The array scalars are somewhat special. So that's what you get when you draw a single element from an array. So if you have a vector called x, and I'm looking at the side column here now, so if you've got a vector called x, and you extract a single element from there, then you get back what we call an array scalar. Now, array scalar is somewhat strange. It's the sort of the bridge between the pure scalar numbers and the NumPy arrays. So the array scalars typically have these types like np.float32, np.uint32, etc. But it's also gotten a data type attached to it, and in many ways it also performs like a NumPy array. So that allows us to bridge the world from the array into pure Python scalars. Moving on to strides. So each array refers to a number of bytes in memory, and those bytes are simply stored linearly, so one following the other. Depending on your data type, a single element in the array may occupy more than 1 byte in memory. So in this example that I show here, I've stored the numbers 0 through 8 in an array, and the array's data type is uint60. So it's an unsigned integer, 16 bits, so it occupies 2 bytes in memory. So every 2 bytes here will store a single value in that array. So 0 will occupy 2 bytes, 1 will occupy 2 bytes, etc., etc. Right, now the NumPy array has got several properties. The first is a data pointer. That data pointer simply tells you where in memory is all this data stored. It's then got a shape. So that shape determines if you interpret the NumPy array from that memory, what are you going to see? So in this case, it's a 3x3 array. So you're going to see your 3x3 matrix. And then the important part, the strides. So the strides tell us if you want to move forward in any single dimension of the array, how many bytes do you have to skip in memory? So for example, if you want to move between element 0 and 1, in our array, that would mean moving from column to column. And you would have to skip 2 bytes in memory. So for each element, to move between 0, 1, and 2, you'd have to skip 2 bytes in memory. So that's why you have a corresponding stride of 2 with the columns. Now, if you want to skip from row to row instead, then you'll see you have to skip from 0 over 1 and 2 and onto 3, right? You're starting off over there, and you want to skip from 0 to 3. So you have to skip 2, 4, 6 bytes in memory. So that's why you see the corresponding 6 in strides over here. Strides are very powerful. They allow NumPy to do a lot of operations without copying data. So for example, here I've got a number of uint 8s in memory. So each element takes up 1 byte. And the number is from 0 to 8 again. And then I've got 2 different arrays, both 3x3, showing those numbers. But in the first case, we've got the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8 running along the rows. And in this example, along the columns. And in this case, I've got them running around along the rows. And the only difference between those 2 arrays would be the strides over here. So here's a question. If the strides of this array over here, if they are 3, 1, what would the strides of this transposed array be? Yeah, 1, 3, yeah. So if you flip the strides around, then the array gets transposed as well. And the nice thing about this is you can flip them around without copying any data in memory other than modifying the strides. So you can take a massive array and transpose it in NumPy without incurring any memory cost. Okay, so broadcasting allows us to combine arrays of different shapes and still get sensible results out. So in this example over here, if you look at the green array over there, that's what I construct in the first line, so zeros of shape 3, 5. The red is an array of just 8 zeros. Now, those 2 can't be combined as is, but if I add an extra axis to x, and I do that by using the np.newAxis indexing operator. np.newAxis is simply the none object, so you could just as well have written none over there. But if I insert an extra axis into x, so I change x's shape from 3, 5 to 3, 5, 1, now it is ready to be combined with the red array over here. And if I then do a combination that, an operation that combines those 2, so x plus y, then it forms an array of this blue shape over here. And that array is of shape 3, 5, 8. Yeah?
What would the stride number be for the new axis? Would it be 1 or 0?
Well, let's see if I can.
Stefan,
Yeah.
could you make the terminal font a little larger so that
Yeah.
in the video recording it's readable?
What's David? This is your PC. What's the best way to do it?
Yeah, so when I bring it up,
Yeah.
down there you can't see it.
That's what you want, I think.
Uh-huh. There we go.
It's
There's
too small.
control plus should do it.
Yeah, it doesn't. For some reason.
Uh-huh.
Like, there's,
There we go.
Yeah.
That's perfect. Yeah. Okay, and then
Good
just
enough, the size?
and then we'll pull this thing up a little bit. Is that high enough? Okay. David? I don't think your NumPy is.
Whoops.
Should we compile it quickly?
No, it's yes, because IPython is not in the virtual end. You just use Python.
Must I just use?
Python, yeah.
You're kidding me. I can't use Python. No.
No, you have to.
I can't use IPython?
I haven't.
Oh
decided
dear.
Python.
Okay, we'll see what we can do.
You just do C today, not Python.
All right. I've become so used to IPython by now, but let's see. I'm going to have to type a little bit more carefully. It's the debug version of Python, which is why you're seeing the refs there as well. Okay, so let's see. So I made an array. What did I use? Zeros? Okay, thank you. 3, 5, there we go. And then 0 is 8. Okay, so these two have shapes that are incompatible. So if I look at X shape and Y shape, we'll talk about it just now, but those shapes are incompatible. Maybe I can show you that slide quickly. So let me just discuss the rule quickly for when things are broadcastable. So when you combine two arrays, and they've got different shapes, you write the shapes underneath one another, and you start comparing them from right to left. So you've got a match when either the dimensions are equal or when one of them is either none or 1. So I've got 3 different examples here. Here we've got an array of shape 5, 10, and 3, 5, 10. Those can be combined because 10 matches 10, 5 matches 5, and 3 is paired up with nothing. So that's fine. And if we combine arrays of those shapes, you'll get out 3, 5, 10. This won't work because here you've got 10 that matches to 10 and 5 that matches to 6, so it's a clear mismatch. And in this case, again, you're fine. You've got a 1 over there. 1s also match anything. So 1 matches 5, 10 matches 10, and none matches anything. So if you combine these two, you'll get out 5, 10, and 5. So now in this case, we've got an array of shape 3, 5, and one of shape 8. So those are incompatible. So if I try something like x times y, yeah, NumPy complains, as expected. So what can I do to fix that? Well, I can either change the y to have a shape of 8, 1, 1, because then the 1s will match up with the 3 and the 5. Or I can insert a 1 dimension at the end of the x array. So then I have 3, 5, 1 matching up to 8. So that's what I did in the example. So I said add a new axis in there. So none or new axis are the same object. So if I index like that, it just adds a new dimension in there. So then, oops, that's not what I want. I want to add it right in the end. So there you go, 3, 5, 1. Dot, dot, dot means take all the dimensions and then just put the new axis at the end of it. You could just as well have replaced the dot, dot, dot with colon and colon. It would give you the same thing. So once you've done that, you've got 2 shapes that are broadcastable because the 8 will match with the 1 and the 5 and the 3, they're unmatched, so they'll be fine. So let's see what happens there. So if I times it with y, there we go. We get a whole bunch of zeros, and the shape of that is equal to 3, 5, 8, as expected. So you had a question about the strides. Who had the question? So did you want to see the strides for y after you added the extra axis, or for x after you added the extra axis? Okay, so x starts off with these strides. So x shape is 3, 5. X strides is 48, which is just, you can compute it if you look at the think it's item size. Yeah, so you see this items are each 8 bytes in memory. So yeah. So 8 bytes to skip from one column to the next, and each row contains 5 items, so 5 times 8 gives you 40. So that gives the strides, and then if you do the indexing, just see that there's a 0 added in there, because you don't actually skip over data on that dimension. Can the dimensions not be multiples? No, they must match perfectly, or it won't do it. Right, so you can also use indexing or broadcasting inside of indexing, which is quite powerful. So in this example, I construct a 2x2 array. Let's see if I can. Yeah. So in this example, I construct a 2x2 array with the elements 1, 2, 3, and 4. And then I construct, so that's the array over there, and then I construct 2 indexing arrays. The first indexing array just contains value 0, 0, 1, 1, and the second one contains a column with 1 and 0. So the question is, what will happen when I index x with ix0 and ix1? And the result is shown over here. So what happens in that case? Well, the first thing that NumPy does is it takes your 2 indexing arrays and it broadcasts them against one another. So if you want to see what that gives you, you call np.broadcast arrays, and you call it on ix0 and ix1, and this is what you get out. So you see that those shapes have now been extended. So you started off with 4 columns and 2 rows. So that has now become an entire matrix of 4 columns and 2 rows. And this gives you the coordinates that are actually used to index the NumPy array. So for example, what would the first element be? Well, it would be 0 and 1. So what you get out is element 0, 1 of your original array. Then the second one would be also 0 and 1. Then you'd have 1, 1, and 1, 1. So that's why you see 2, 2, 4, 4 over there. Okay, is that roughly clear what's happening there? Okay. Now, yeah. So you've got an array of shape. The first ix0 has got a shape of 1, 4. And you're now combining that with an array of shape 2, 1. So the output would be 2 by 4. And so it duplicates those elements in order to give you a 2 by 4 array out. And that's what is used to index over here. Yeah. So one corresponding to how ix0 is modified. I mean, it's not actually modified in memory, but NumPy views ix0 in the new shape. So this is the same thing you would get when you add 2 arrays like that together. So it's equivalent to the example we just saw. If you take 1, 2, 3, and you take a column vector 1, 2. This might be a little bit more intuitive what's happening here. So x and y, if you add x and y, you'll see that x is duplicated. It becomes 1, 2, 3, 1, 2, 3. So it duplicates that row. Y, that column is duplicated, becomes 1, 2, 1, 2, 1, 2. And then those 2 are combined when you sum them. Now exactly the same thing happens when you index. ix0 is duplicated, and ix1 is duplicated in terms of columns. And then they're matched element by element to give the different coordinates that index into your original array.
So it seems like that stride of 0 is kind of pinnacle.
Oh, yeah.
So
not a copy for the Yeah, zero strides are super important because it allows you to take a very small amount of data and blow it up. So what in MATLAB would be something like repmat, where you would make copies of the data in memory. With a zero stride, you can use the same data over and over again without copying any data. There is, if you want to play around with striding yourself and see a little bit what it does, there's a numpy.lib.stride tricks library. And that's got a method as strided that you can use to modify the strides of an array and see how it affects the outcome. You can also, when you do indexing, you can use the colon and the ellipses, but I would recommend against that because the output gets a little bit tricky to explain or to predict when you're starting to broadcast arrays against colons and against ellipses. All right, so that's sort of a very brief overview of some of the core concepts in NumPy. I'll hand back over to David now to discuss how to build NumPy.
So if I so then understand the output of NP.broadcast when you run X, Y now.
Yeah, so what was the question?
So the X and Y you just defined.
Mm-hmm.
I did NP.broadcast arrays. I don't understand what from that. Oh, because I didn't put.
Because you have two arrays in the input, you have the output, like each array which is broadcasted. So if you had like 3 arrays, you would have like 3 arrays in the output. That's why you have 2 arrays in the output. Is that your question? Why you have like
Yeah, but
arrays?
this output looks a bit strange. It doesn't duplicate it in broadcast arrays.
I mean, I did it without the extra brackets.
Uh-huh.
That's something else.
Well, when I look at the output now, it doesn't. This doesn't look exactly like what I would have expected.
So I did it with, I didn't put 2 brackets.
Oh, just the one? Oh, maybe. Oh, there we go. That's perfect. So let's call those XX and YY. Yeah, I just add an extra bracket in there. So if you broadcast X versus Y, then you get XX and YY. So you'll see that it duplicates the rows and the columns appropriately. Right, thanks, Dave.
Okay, so so since we want to like work on the NumPy C code, obviously we need to be able to build it first because we won't be able to get very far. So like there are like 2 ways to build NumPy, more or less. And the simple way is to just use like if you just want to install NumPy to use it, the simple way is to just use the default method of building it, which is using distutils. And to use distutils, like maybe most people here have built NumPy at least once. If you want to build it like just for like debugging or like testing something, then you just do an in-place build. And the way to do in-place build is to just, you call whatever Python you want to use to build NumPy against. You call setup.py, build ext -i. -i just means in place. It means it will like copy all the C extension in the right place inside the source tree. So that like once this is successful, you can just import NumPy directly from the source tree. You don't have to install it. Especially when you want to debug something, you don't want to have to install NumPy every time. So in-place build is the right thing to do in that case. And then you can just run the test directly, at least again in place, to do. So NumPy test read is based on nose test. You just execute nose test, for example, NumPy/core. So we'll see later that most of the actual C implementation of NumPy inside NumPy/core. So if you just want to test that part of NumPy, you just do nose test NumPy/core. So, So for people who don't use or can't use a Vagrant VM, for some of the things, it will be easier if you can just use a debug version of Python. So like on this VM, I created a virtual env, but with a debug Python instead of the normal Python. So the debug Python is not optimized when you build it and contains all the debugging symbols that are useful when you need to run the debugger. And so here I just have, so at that point I just have a pristine NumPy source tree. So I just did a git clone of NumPy, and if I simply want to build it in place, just do this, it will take a few seconds. And once this is successful, I get back all the C extension will be built and put into the source tree, and you can import NumPy directly from there. So that's nice and handy, but one of the issues with distutils is it doesn't handle dependency very well. So again, when you just want to use NumPy and install NumPy, that's not a big issue. But like when you develop on NumPy, you don't want to build NumPy from scratch every time. So for this reason and other reasons, I started working on a parallel build system that allows you to basically build things more quickly, and also like to build more quickly, and also like to handle dependencies correctly. That is, if you change one of the header file, it will automatically get up, oh, okay, I need to compile this object file, but not the rest, and it will give you a reliable build that you can't really have with distutils. Oops. So that's another slide to remember, like for later for the exercise. So slide number 28. Again, if you have the VM, everything is set up directly. But if you don't have the VM set up, then you can just use this instruction to set up so Bento, which is the name of the build tool. So just to summarize the instructions, so I just first download Bento, which is a Python package that you need to build NumPy. Then I install it at the second line here. Then Bento needs another tool to actually do the compilation, which is called WAF. Then you just need to export this environment variable to say where to look for WAF. And you need to do that only once. Then every time after, you can just build NumPy. And the way to build NumPy is to use this command here. So instead of calling Python setup.py build extra, you just call bento maker build, and here again -i is in place. So if you do just that, you have like 5 lines instead of 1 line, so it's definitely more complicated and maybe not worth the overhead. But once you start developing, then it becomes much more interesting. So one of the reasons is first, Bento supports parallel build. So like if you have 8 cores, I have 8 cores on this machine, then you can just say, okay, I want to build with, okay, here with 4 cores, just like the make option, J4, I build with 4 cores in parallel. Another thing that is useful is that if you modify just one C file, you will just recompile this C file and build the new extension, but it will not rebuild everything. So actually, distutils doesn't rebuild anything. It doesn't detect the dependency changes. So when you start changing things regularly into NumPy because you want to fix a bug, or you just want to understand how something works, using distutils is kind of a pain. Like basically, the only reliable way is to just scratch your build tree and rebuild everything all the time. So unless you have a very powerful machine, that's not something very enjoyable. And one last thing that is pretty useful with Bento is it's very easy to modify, to customize the compilation. So here in the last line, I just want to compile NumPy with Clang because Clang gives me better like warning and error message than GCC. And here I want to build a special debug build, no optimization, -g, keep all the debug symbols, and I want some extra warning because I want all the extra warnings that I can get from Clang. Okay, so since pretty much every exercise after this one will deal with building NumPy, well, it's important to be able to build it first. So like one first kind of very easy exercise is, well, it's mostly to make sure that everybody gets the environment set up, is to just try to build NumPy from a NumPy checkout. And you can see that if you build it with a few warning flags, you get a lot of warnings. So the first exercise, the goal is just like look at one file with 1 or 2 warnings and try to fix them using Bento. So I give you like a few minutes to like basically build NumPy. First, just build it naturally, and then try to like modify some source code to like fix some of the warning you get into the output. So some of the warning you see often in NumPy is this kind of warning here, where it tells you basically that, oh, okay, like you have a function with 3 arguments, sorry, no, not 2, self and args, but actually you're not using args. So like, yeah. Oh, no question. So here you have a function, a C function in the light module module. You have 2 arguments, but actually you're not using the second argument. So when you give a lot of warning flags to most compilers, they will give you a warning if you have a function that takes argument and you don't use the argument inside the function. So you have like, I don't know, like maybe hundreds of warnings like that into NumPy. So because of that, gives a lot of like false alarms. So the thing we have in NumPy source code is to have this special macro, NPI unused, that use some like kind of semi-hack, which are compiler specific to say, yes, I have this argument here, but actually I guarantee you I will not use it. So for all the arguments we don't use inside functions, we need to declare those functions because those are like public API, maybe from the Python C API, so we cannot just modify the signature. We want to specify to the compiler, well, trust me, this argument, I will not use it. If you decorate it with API unused, then the warning is disabled for this one code. And the reason to do that is because if you have like too many such warnings, then like you miss like actual warning that give you warning against something that may be actually meaningful. So the goal of like trying to get rid of those warnings is just to get rid of the false argument. And here really the goal is just to do a very simple modification of the C code and to try to get it running on the machine.
So are we supposed to actually try this exercise?
Yeah, yeah.
How do we know if it works?
Oh, that's sorry?
How can we tell if it works? Because I mean, I tried this Bento maker build -I and it just returns without doing anything. Is that what it's supposed to do?
I'm seeing something similar.
What is it supposed to be doing?
So like it builds everything.
Yeah, I know, but where does it get the everything to build? No, I think I've missed a step.
So
Can you show them a build?
yeah, sure. So maybe like it may be my fault because I built NumPy before giving the VM. If you use the VM, like where do you see that output on your machine?
They're in my terminal.
Okay. Well, because if everything is already built, then it will not do anything because everything is built already.
Do you have a NumPy git directory?
So you should get this kind of output the first time you run it, right?
Where are you running?
Well, you run inside the NumPy source tree, right?
That wasn't on the key that you gave us. I was supposed to find it. Sorry, I think I missed that slide.
So like inside the USB key, there's like one VM. So if you want to use a VM, then you start with VirtualBox, you start the VM. And then inside the VM, you have everything set up. If you don't want to use the VM for some reason, because you don't want to mess with the system, then you will need like to clone NumPy and do everything by yourself.
Yeah, okay.
Sure.
I missed the step that said how you find NumPy. I don't think it was in the slides.
No, it's not given you right. It's a mistake. So,
So I guess also people need to have VirtualBox installed to be able to...
yeah, there is VirtualBox on your USB key. There is a, yeah. Yes, it's vagrant. There is a text file that says, like, it's just vagrant.
was trying to use setup on OS 10. I had to downgrade to pull that to that as well. Virtual binding.
Okay.
Yeah, 2.14. It basically winds.
Because I mean, on Linux, generally, like the environment is easy to set up that simple enough that you don't really need the VM if you're familiar with GCC and these things. And the VM is mostly useful on Mac because then it's a bit more difficult to set up the environment. But, so what I will do, I will just give the instruction to clone NumPy a directory, and then we'll try to, like for people who have like some issues, we'll pass on and try to fix them for you. So yeah, to clone NumPy source tree, so this you do anywhere you want. So just git clone on github.com/numpy/numpy. And this gives you back, so this may take like 1 minute or two. And then you just inside the NumPy source tree, and then you need to run either the Python setup.py build -i inside this source tree, or the bento inside this source tree as well. Yeah. Yeah. No, it's my fault. I haven't explained it very well. Yeah.
Can you quickly show this URL for cloning bento?
So the easiest is just to get to this URL, which has the slides, so that you can see that slides all the time. And
Somehow it's not showing up in.
Yeah, I'm getting a 4 error.
So I didn't understand what the virtual machine is for.
so the virtual machine is for, like, if you don't want to, like, I don't like to, for people who don't have a development environment set up. The VM contains everything. There's like GCC, all these kind of things, with the right Python development headers, all these kind of things. But if you know how to do that, then you don't really need a VM.
I don't know if I don't understand.
Well, if you don't know, then you don't, right?
Well, I mean, I use GCC and things. Because, I mean, I already have other things that I use.
So, like, have you built NumPy before? Or?
I mean, I've just run Blender Maker family as well.
You need to have it.
Okay. Well, I couldn't get a virtual machine to work, but I just did.
Well, I
make a thing and
like,
it worked.
the VM is just a way to get things working.
Okay.
Anybody needs an older version? I don't know.
So it doesn't say for the. Yes.
It's just, at the end, like, if you have a builder or something, it's just building things.
Oh, and then I.
Like I've